Thank you very much to all of you for attending this event. This is not our last event of the medical section of the year. There will be another one in December. Um, I'm just going to do our annual general meeting for the Royal Statistical Society medical section for this year. This should be very, very quick. So my name is Ruth Vieira. I'm a senior lecturer at the University of Aberdeen, and I am also the chair of the medical section committee. So the committee is made of 12 members, and we all represent different fields within statistics. Some are from industry and academia, NHS, and also independent consultants. And we also represent different areas of the UK currently. So the remit of our committee of the section is to develop and support the application of statistical methods in all branches of medicine and healthcare. So we do have different objectives that we try every year to fulfill. So mostly we organize high quality meetings, but we also try to contribute to income generation through the events registration. So for those that don't know, the Royal Statistical Society is a charity. We contribute with articles to the magazine Significance. We try to support the professional development of medical statisticians, among other things. So this was a busy year for the section. We organized 6 different sessions, 2 of them for the RSS annual conference. We were also very busy with sharing and sponsoring 2 RSS discussion meetings. We've screened for discussion papers, and we are also working as associate editors for discussion papers. We also participated in the judging panel for one of the RSS awards, the Florence Nightingale, among other things. So every year we have to say goodbye to a couple of our members. So this year is just one member, which is Oliver Hugh from the Perinatal Institute. So really thank you for your contribution during the past year. And as always, we need to thank Paul Gentry, Amira Chaudhry, and Janina Sassin for their amazing support throughout the year with our activities. So for 2026, there will be some small changes. We will have 2 new members. So that is Ryan Daniel from Cardiff University and Penny Reynolds from the University of Florida. So we are extending our boundaries. We are becoming a more international committee. And we will also have a new meeting secretary, and that will be Dr. Simon Day. So these names for the committee for 2026, they will be posted in our website. And if you would like to provide any feedback, please email me or Jason, our secretary. After 1 month, then they will be approved. And finally, if you'd like to get involved with the medical section, you can subscribe to our mailing list. So that's the website, and you can also follow us on social media. And that's all from me. Thank you very much.
It's a great pleasure to talk with us today, Professor Stanghellini. Professor Stanghellini works at the University of Perugia and is also a visiting professor at the University of Pune. Her expertise is in graphical Markov models, and she is going to speak today about some recent contributions to handle selection bias in observational studies.
First of all, I need to thank Dr. Cristiana Canzolanchi for the invitation to give a seminar to this venue in Oxford, and I need to thank the Royal Statistical Society for the medical section in the Oxford local group. Now I'm going to talk about some recent advances in the when we want to handle with the selection bias in observational studies. And the first thing I want to do is to acknowledge the colleagues that work with me on these issues, and among them Marco Doretti from the University of Florence, Taiki Tezuka from Yokohama National University in Japan, and Minna Yembak from Umeå University in Sweden. Right. Selection bias. Selection bias arises when the sample cannot be considered as randomly drawn from the target population. And the participations of units in the sample depends on the phenomena we want to investigate. Why can this happen? There are many reasons. But I just quote some of them. One is random sampling is not feasible, and I will give you a practical context where it wasn't. Or if it's feasible, then units fail to comply either partially or fully. So they just do not participate since the beginning. So clearly conclusions start based on the available information, the so-called complete case analysis, are necessarily distorted. So start with some definitions. I just now focus on causal inference context, and then maybe make some comments in the end. I think there is, we in this context, the general setup is that we have a treatment with two levels, A0 and A1, and we have an outcome of interest, Y. And we denote with Y bracket AI the potential outcome of Y under the treatment small AI. We assume that we have a set of confounding sufficient covariates such that the assigned treatment is independent from the potential outcome after conditioning on this sufficient set of covariates. And for now, I just define the causal estimand as the conditional average treatment effect, which is the difference of the expected value of the potential outcome under the two scenarios. When Y is binary, we also have other measurement of interest, such the relative risk or the odds ratio. Now, what is the observable distribution in this context? I just introduced a selection indicator with value 1 if the unit is in the study. And therefore, the observable distribution is just the probability of Y given A, C, and R equal to 1. Now, if we assume consistency, then when the treatment takes the actual value AI, then the observed Y is actually the potential outcome under Y AI. So that's consistency assumption is also useful, and is the usual assumption usually made. So the question now becomes under which conditions delta is identified from the observable distribution. And I'm now focusing on A binary, but the assumption can be removed, and I actually show an example where it will be removed. Now, since the seminal work of Hernan and co-authors, basically the directed acyclic graphs have been the main tool to understand under which condition there is a selection bias on the causal estimates. In this setting, the binary indicator is introduced as a node, and the directed acyclic graph represents the data generating process in the population, so before selection. And a very big number of contributions exist to check via the graph whether identification of delta is possible, both in parametric and non-parametric context. And the literature is really huge and difficult to just give just one reference. Now, I will, the structure of this talk, I will focus mainly on recoverability of delta under various settings. and I will present some identification strategies when some auxiliary information is available, and in particular, I will focus on two cases. The first one is when we have a bias breaker node, which is available and measured only on the selection affected sample. And the second is when we assume that A and C are measured on a random sample from the target population, whereas Y is measured only on this selected sample. Of course, we need to add some complementary assumptions in both situations. So let's start with the first. The first is when we assume that we have a bias breaker node, binary bias breaker node, which we call V. And the situation is as the one depicted in this directed acyclic graph, where we have, again, the set of categorical variables C. And the important thing to notice is that this V node is actually separating both the treatment and the response from the selection indicator. So if we have these, then with this assumption, we can carry on with non-parametric identification of the causal effect of A on Y. And we may assume that C can be partitioned into two subsets, one which is not influencing R directly, and the other one which may be influencing R directly. So if the population prevalence of this node, given the subset of variable C prime, is known from external sources, or can be made the object of a sensitivity analysis, then non-parametric identification of this effect is possible. Identifiability of causal effects, the sense whenever C is confounding sufficient. So let's look at the algorithm, which allows identification. We take the odds transform of the probability of V equal 1 in the selected sample. And we know this because we have information in the selected sample. And we use the knowledge of our prior prevalence to form this ratio here. And we also form the odds transform of this P of V given C prime in the selected sample that we also have. And then we identify these odds of P of V equal 1 given A and C as the product of the odds previously defined, and this ratio 1 over Kc. Then we revert to the probability scale, and then we identify the probability of Y given A and C because of this conditional independence, because we postulate that this is equal to the one on the selected sample. And eventually, what did I do? Sorry, I wanted to take rid of this. I don't want this one. Okay. Okay, thanks. Right. And eventually, the probability that we want is as the sum of over the node V of this product of these two probabilities. So another look of the intuition behind the equation, which is the crucial equation that leads us to identify this effect. Well, it's first from standard probability results. We know that the probability of V, the odds of V given A is equal to the odds of V given A in the selected sample times the relative risk of R equal to 1 given the V equals 0. What's the problem? Sorry. At the full screen, yes. Yep. Sorry, thank you. But it's now it's not sure. I say plus in the mixture of these two words, line and okay. So, and if we assume that the bias breaker assumption is that this relative risk here is actually does not depend on A anymore, and then because of this not missing dependence is equal to this, which in turn is equal to this product. So the P of V is actually the prevalence of V in the population. And this equation has been widely exploited in the case control literature and is well known in that context. Now, why, let's say, P of V can be fixed? So is there anything wrong again? Sorry, it's okay.
See your video online.
Just. Oh, what happened? Oh, you should go. Sorry.
No matter what, I want
Just look like it's fine. So, else is everything all right? Yeah, okay. So, usually, this probability of V given in the sample, given the covariate, may be fixed by design. For instance, in stratified case control studies, where V is the primary outcome. So V may be the primary outcome in stratified case control studies. And what happens is actually, so this is the primary outcome, and Y becomes the secondary outcome in stratified case control studies. So this may be fixed by design. And this, because of this relationship, there is a clear link with secondary outcome in stratified case control studies. The second thing I want to note is that C prime has to include all AY confounders directly influencing R and not necessarily all parents of R. And when A is directly influencing the selection indicator, then we need from standard case control results, we need the prevalence of V according not only C prime, but also A, which is clearly more difficult to gain in applied contexts. Related work. Now, this work is a generalization of the one in generated and co-authors to the situation of Y having any nature. They just postulated Y being binary. And I owe this to the determination of bias breaker to their work. So that's not our definition. It's very effective definition of bias breaker. So we borrowed this idea of a bias breaker from them. And there are also links to the stratified case control literature as a secondary outcome again. And I just put some quotation. One is van der Laan, who did a lot of secondary estimation of secondary outcome, and also Christiana's work with David Cox, basically in the context of regression analysis. And it's also linked to mediation analysis because Y may act as a mediator between on the pathway between the treatment and the philosophy. So there are links to this branch of literature. We propose the parametric estimation methods, both based on maximum likelihood and estimation, and the details are in a paper that I just referred to. Non-parametric methods can also be formulated, and maybe some interesting things may come also from this kind of literature. And just to give an example where this work started, we have in Italy, we had in Milano, which is Sacco Hospital, established a day hospital for long post and long COVID patients. And since it was meant to be a therapeutical laboratory, it wasn't really feasible to do any kind of random sampling or stratified random sampling. And we wanted to check several aspects. I'm just focusing on the easiest one, but there are many others, and we're still doing research on these aspects, because ultimately the main goal of this hospital was to understand the possible determinants of post and long COVID syndrome. But for now, we started with a simple situation where we assume that we want to study the effect of obesity on the severity of the COVID-19. So Y is a binary variable that takes two levels, severe or critical form or not. And why we wanted to do that? Well, because there are also several studies on this effect. So we wanted to check whether our assumptions could be confirmed. So we assume that actually appearance to this post-long COVID hospital was driven mainly by having at least one symptom, or maybe being in that hospital and going there would be because it was advertised as a post-long COVID hospital, maybe the only driving possibility to enroll into this laboratory. And then we assumed that actually this would separate being obese and having the long COVID, having developed the COVID in a critical form. This could be separated from R by this node P. And then we performed some preliminary analysis under these assumptions, and we postulated the prevalence. We didn't know exactly the prevalence, but we made it changing. This is the prevalence of post-long COVID syndrome in the population, and we let it change from small values to quite a large value, 0.5. And this is the estimated effect of the obesity across when the prevalence is varying, which is above 1 on the Logos scale, so 1.2, which is actually online with the literature. And this is the naive estimator. So the naive estimator is the one that's the complete case, basically. So this is sort of reassuring, but and this is why we wanted to start with this simple example, because then we want to carry on other aspects concerning the post-long COVID syndrome. So, but it's useful to use the directed acyclic graph also to speculate about different mechanisms driving the selection model. Sorry, I had another slide. Sorry. Yeah, sorry. So, for instance, suppose that Y, having developed this COVID in a severe form, would actually influence appearance in the lab. And then it is possible because we are in a binary context. So we can sort of say that the odds ratio here is identifiable if this situation is possible, because that's the standard situation of case control studies. We just forget about V, marginalize over V, and just do the standard complete case analysis. And that's the odds ratio is identifiable. So that also explains why, for instance, the odds ratio in the complete case analysis is not very different from the one modified by using the prevalence. So what is actually forbidden is this direct arrow between obesity and being in the COVID and in the day hospital. That's something we don't want here. We can speculate. We can say, okay, if it's positive, suppose this is positive, suppose this is also positive, then we are actually underestimating the true effect. We can speculate about this, but if we do not have any information on the how big this arrow here, then that's all we can do. So that's actually a situation where, yes, we can do something, but not, we have to rely on the absence of this direct red arrow if we want to carry on with our analysis. This is the second part of the talk, which actually is saying, no, let's suppose that I know A and C on a subset, on the individual, the full random sample, but Y is measured only on a subset of patients. And here we restrict to Y being binary. Maybe there is also a way to sidestep this, but we haven't found it yet. So we restrict to Y being binary. And well, actually, there are many ways, but not in this context. So we assume Y being influenced by A and this covariate set C. And we now postulate a similar logistic model for the driving indicator R against AC and Y as well. We assume here that Y may drive the appearance in the selected sample as well. And this is linked to Heckman procedure. That's although for Y binary, Heckman procedure presents a lot of problems, its stability and so on, but it's and actually we wanted to develop since the Heckman procedure is based on the probit model and the underlying normality of the errors, we thought maybe we want to develop something which is more linked to the parametric logistic and non-parametric, semi-parametric logistic form. And under the testable assumption that the outcome is either very rare or very frequent within the strata of A and C, then we can develop something similar to the Heckman-like procedure. So let's say, let's discuss the framework. We have a semi-parametric logistic model for Y in the population, and we are interested in the effect of A after conditioning on the covariates. Then we have also a semi-parametric model for the appearance in the population, which can be also a function, in principle, a function of Y. And we write it as some linear form, let's say linear parameters form, and a parameter delta Y, which is linked to Y. So the corresponding directed cyclic graph this time is as depicted here. We allow for this A to Y arrow, which was the one we didn't want before. So now, if in the selected sample we are conditioning then on R equal to 1, we know from standard probability results, the one I've used before, that this is the conditional logic model is equal to the marginal logic model plus the log of the relative risk of R being equal 1, varying Y, keeping fixed A and C. So this is actually the relative risk of R being 1 when Y varies and the covariates and A are kept constant. Now, these terms plays the role of the inverse Smith ratio in X1 model because it depends on the selection parameters. So if you account for it, then you're back to what you want to estimate. But unlike the inverse Smith ratio, that term here cannot be immediately obtained from the observed distribution because you need to having the joint distribution of R and Y in order to form the relative risk, and we do not have it. But after a trick, a bit of other work, we know that marginal of the probability of R equal to 1 in an A and C is equal to the conditional 1 plus the log minus this time, because we need to detract the relative risk of Y when varies R. And this time, which actually in a different setup, we can also take this away. But this time, this can be approximated and can be estimated from the data because you can use a sort of approximation of this log relative risk towards the log of this term here. And if it's either very big or either very small, depending on which one you want to use, then this approximation works well. And the nice feature is that if you now, this is the probability of y equals 0 in the selected sample, is something we can measure. And this is the probability of y equals 1 in the selected sample, and it's again something you can measure. And you can sort of include it as a covariance in this equation. And the nice feature is that the coefficient is actually depending on the delta y. Sorry, so there is something that, okay. So the idea is to obtain an initial non-parametric or semi-parametric estimate and insert it as a covariate in the first equation. Sorry, I had to run it twice, but I didn't. So we insert it as a covariate in this equation here, because we use this approximation. And then we get a correction term, which depends on delta y. We use delta y to build the second offset term to be included in the outcome equation. Now, standard errors can be calculated using sandwich estimators or bootstrap methods or whatever. There are plenty of different methods. Of course, a maximum likelihood approach is also possible via expectation and maximization, but we run some preliminary simulations which suggest that the Heckman-like strategy might, in some context, outperform the maximum likelihood. And in parallel to the raw parameter for the Heckman-like procedure, delta y is actually likely to suffer from weak identification, especially when the sample size is small. Okay, last part, application to the silver split in Europe. That's a data set that comes from the European Survey on Health, Aging and Retirement, the so-called SHARE, which is a routinely conducted survey on elderly people in 28 European countries and Israel. And the idea from the demographic point of view is to look at silver splits, which are union dissolutions among people over 50. And the idea and the interest in the dyadic role of wealth, examined together with other social demographic factors, and in particular, the interest lies in investigating the presence of gendered patterns. So we looked at this data. We looked at the wave 6, 2015, and subsequently observed splits at wave 7. We have more 11,000 heterosexual couples at the baseline, and we just focused on the ones with both members alive in 2017. Now, of these, about 8% dropped out from the study for various reasons, maybe, I don't know, maybe linked potentially to the split. So we cannot exclude that the dropout from this example in this database is actually not informative. We need to account that it can be informative. And among the remaining couples, the marginal split rate is small, around 14%, which satisfies the rare outcome assumption, also within levels of the explanatory variables. So that's the final model. This is the outcome equation for Y, and this is the selection model for the probability to give information on whether or not, to be in the sample, R equal 1. And talking about the selection in the selection equation, we see that the duration makes it more likely to be in the sample. Yes, the household size is not, or is also making most likely to be in the sample. Belonging to a northern country makes it less likely. Number of children more likely, and so on. And actually, we also have this delta y, which is negative and actually is non-significant. So basically, there is, according to this analysis, there is no effect of y on the probability to be in the sample. So then we keep the outcome model with the intercept and the age duration. And actually, the demography, people found it particularly interesting, this variable here, which is the difference in education between the man and the female in the couple. The difference, the more the difference, the higher the difference, the less likely is to have a silver streak. So that's something that may be interesting. In this situation, there is no evidence of informative selection. Extension to longitudinal models may be rather straightforward if you allow, if you, for instance, think of some data generating process like this, where responding at the first weight, so you have Y and R at the first weight, then at the second, and you assume actually that the response depends, the two response rates are correlated, but it becomes a bit more tricky when actually under the reasonable assumption that actually Y1 is highly correlated with Y2, actually Y1 is influencing Y2. So that's becoming a bit tricky. And also, unless we just focus on monotonic dropout, which is probably not so interesting. And then it's currently under investigation. But actually, I wanted to point out that in this situation, there may be a path from A to R1 to Y2, which all creates some questions, because then you may ask whether changing the strategy, the R1 sample, the actual sample, would also change. And indeed, when R is on the pathway from A to Y, other effects may be of interest, where, for instance, the effect, which is denoted by DRA, of the expected value of Y under the situation that the potential outcome of R is equal to 1, which is the counterfactual sample under A1, minus the same under A0. Why do we need that? Well, because this Ri is now on the way from the treatment and the outcome variable. So we can potentially be interested not just in the actual sample, but in the counterfactual sample, where Ra is equal to 1, which are the units that will be in the sample under the two scenarios. So more generally, we may be interested in, we may be interested in effects like delta S, which is the difference between the expected values conditioning on S, but now S is a combination of both factual and counterfactual variables. And this opens new problems. And there is a nice paper based on the use of single word intervention graph by Matter and Spitzer on these topics, which is also interested because it's also linked to survival analysis and so on. The thing to notice is that if the population change, this is not a causal effect technically, because the population under the two scenarios may be different. Nonetheless, it's a very interesting effect, which may be worth to investigate. So to conclude, selection bias is actually an identification problem and therefore cannot be solved by increasing the sample size. I know the audience here knows this very well, but sometimes you may hear someone say, okay, just increase the sample size. No, if it's a problem it's again an identification problem. And it's relevant not only for causal inference, but also for association and prediction studies. So you just cannot say, okay, I'm not doing causal inference, so I just forget. I find directed acyclic graphs very helpful in formulating the problem and discuss violation of the assumptions. And I think it's also very relevant on the views of fairness. There is a lot of research on the fairness of algorithm, of artificial intelligence algorithm, and they are also very affected by selection bias. So I think that's all. Thank you very much for being in the audience, both online and in presence. And comments and suggestions are more than welcome. I just give you some references, essential references, where I think this is the paper that I mentioned on the bias breaker by Sara Ginelletti. This is also the paper on using the R indicator in the directed acyclic graph. It's the first paper, to my knowledge. And then, of course, the Heckman sample selection bias as a specification error, Maslow Shifter, Christiana Karsonaki and David Cox on this regression reconstruction from a retrospective sample, and actually the paper where I published this algorithm and many others. So this is a really very, very essential reference. I can leave it to you. Thank you very much.
Are there any questions in the room first? Or if you have any questions online, can either unmute yourself or write in the chat.
Yep.
I'm sure in your COVID, believe you take your 10 different medical words. The persons are near. How did that make you? How was that? That words, what were other?
Yeah, thank you. Thank you for the question. Right. So the question is, in my example of the long COVID hospital, R equal 1 is appearance at the lab, and what is R equal 0, right? R equal 0 is the people who are actually affected by long COVID, but do not come to the seminar, to the lab. They go elsewhere, maybe. So the people, sorry, no, that's imprecise. The people who had COVID, and went elsewhere. So they might have or not have long COVID, but just didn't go to the lab. Yeah.
Although,
Sorry?
no, wait.
Yeah.
But you start to come all the other hospitals in microphones in order to see how correct your estimate was. You think behind it. In principle, that can be clarified.
In principle, yes, but there still may be people who do not have COVID, long COVID symptoms, then don't go anywhere. So R equals 0 is not just, is all the people who had COVID and never appeared anywhere. You follow me now? Yeah. So I'm not conditioning on the group of people who had long COVID. I think I want, in principle, I would like to condition on all people who had COVID and reach all of them, which I know hospitals made it, but they focused only on the people who have hospitalized, and then they reach them up. So that is possible and has other problems because these are only the hospitalized people. So they can contact. I know, for instance, in Florence, they did, and I actually had this this data again. Also, in some other part of Italy, they did it. They just be in contact with the patients they had, and they asked for a follow-up, right? And that's upsetting the population who were hospitalized. So it's a very good question, but in principle, we didn't want to concentrate only on the population who were hospitalized. We wanted to understand the whole mechanism in the population. A lot of people, as here, I think, had COVID without going to the hospital, especially in the first wave, because that's where the hospital were under big pressure, and they were told, please, if possible, don't show at the emergency department. That time of for us was a demanding time, I think, in truth. So a lot of research needs to be done. We haven't understood a lot of these things yet. Yeah, and this hospital is actually, the idea was also to understand what creates this post-long COVID syndrome, which is also a bit tricky to understand. But then you have to take into account this problem of self-selection again, right? Thank you for the question.
Fine. I don't. And I watching says, thanks for this excellent talk. I have a question about the UG hospital based study. Was it a 1 day cross-sectional survey begin hospital follow-up?
It was a 1 day cross-section. No, it was a longitudinal. It was a longitudinal. It was a longitudinal, and then we focused on the first appearance only. But it's a very complicated. That's why we wanted to extend to more waves. Yes, it's a longitudinal structure. Yes, there is a question from the audience too. Yeah. Sorry, can you speak loudly?
Don't put no safety of association with data instantly. So I mean, when you would show the results of the market, they must be necessary to create some bundles with when what see the things you was nice. And if you put it out, very between them both, maybe say same way.
I'm not sure I understood. Can you just repeat? But just because the sound here, the noise is a bit
Right?
Yeah.
I'm sure how to put the bubble, you have to set me and wait it. Put the kilo water shape of the section to the so perhaps if you about several people's basic marks still on set up with animals and but you actually obtain the tiny market and if you represent the population base, and you know saying that you can hire the in your set a selected from sleep with it.
That's a good question. If I understand it, how do we rely on the confounding set that we have? Is your question?
And I'll keep it safe with substitution.
All right. And okay. Well, that's a very interesting question. Actually, what we do is that we use what we have and we look at the marginal association between them. Then we are in a selected sample again. So it could be that if we see something, it could be induced by the selection mechanism. So it's a bit, that's, I understand it's a bit the trickiest part. I would say also if you want to be causal in the sense that you think this is a causal effect, but then, yeah, I agree with you. It's a bit the trickiest part of it. Thanks for the question.
Says, in practice, how can researchers identify and manage selection bias in observational studies? So,
In practice, how can researchers identify and manage selection bias in observational studies? Very good question. I find the directed acyclic graph very useful. And also because you can speculate on the direction of the bias induced. So how can we identify? Well, if we do not have in the first context, we can postulate it and then investigate violations on these assumptions and their effect on what we want to estimate. If we do have some covariates, or if we have, like in the second example, then we can do better, we can do more because we have more information. So at least run a selection, a selection equation against the covariates and see if some of them are actually significant or not. Bearing in mind of this terrible effect of compensation with any different effects that can be non-significant just because they compensate each other. So it's a very good question. Yeah, thank you. And in practice, I again, my suggestion is just speculate on possible sources. Use this is perhaps my bias. Use directly the circuit graph because then you see the underlying mechanism.
Another question by Ryan Andrews. The suggestions for analytically addressing selection bias that occurs pre-enrollment. We want to answer a question about an entire population of interest was study data you have generated after applying enrollment station. Actually, I have no data of those who are expert. I don't need to include it.
Sorry? I read it. Shall I read it? Can you read it? I want to answer a question about the entire population of interest, but study data we had was generated after applying knowing excluded criteria. That's a terrible. That has to do with the portability. Yeah, tough question. There is transposability issues here. As far as I know, I'm not an expert, but transportability has to rely on assumptions, and you have to trust the assumptions. This is my impression. There's a lot of work which is on this issue, which is again transportability of effects from one subject of the population to the general population. Because the subset is, and we know the criteria. Yes, we know the criteria, that the advantage, but again, you have to speculate on the relationship between on the effect of this known criteria on the general population. But I'm not an expert on transportability. Yeah, this question. Thanks.
Thank you very much, and it was a great talk. Thank you very much, everyone here and online for attending.